How you doing, guys? I'm Paul Lim. I'm the Director of Engineering with Forterra, and with me is Bram from EMCON. Today we're going to talk about the evaluation of cracks that you might see in concrete pipe after it's been installed. Now, in the early days, this is how we tested concrete pipe. You loaded it up trying to simulate the loading condition of a buried pipe, and you evaluated how it performed by measuring cracks on it. Today, we use what's called a three-edge bearing test. So any plant that you go to in North America is able to test their pipe by using a crack criteria. And we have to be able to test every size that we make. So even the largest 3,000 millimeter pipe, we have equipment to test those sizes. Now, the two things we're looking for during this test is what's called a 0.3 millimeter design crack, and that's what this gauge here represents. So you can see it's not a very wide crack at all that we're looking for. And then the other criteria is the ultimate strength of the pipe. So we have to know those two things for every size and every strength class that we manufacture. Now, the thing to keep in mind is that 0.3 millimeter crack, this gauge here, does not mean that the pipe has failed. We actually end up stopping the test at this point and putting that piece of pipe back into the yard. So a lot of times when you're on a job site, you might actually see a piece of pipe that is painted as a test pipe or a 3EB test pipe. And what that's telling you is that particular piece of pipe was used for this test during the manufacturing process, and we just put it back in the yard. So it's a non-destructive test that we do with this criteria here, the 0.3 millimeter crack. Now, instead of deflecting while you're loading the pipe, what the concrete pipe does is it creates tension and compression zones in the wall. And that's where we expect the cracks to appear, is in those tension zones. So we all know that concrete is strong in compression, but weak in tension. And that's why we put steel in those tension areas of any concrete structure. So concrete pipe is no different. The thing to keep in mind also is the crack that we're looking for during this test is 1/5 the size of a dime. So again, we just want to stress that this is a fine hairline crack that we're looking for, and it does not change or alter the function of that pipe. Now, what that crack criteria tells us is what the strength class of the pipe is. So when you buy a pipe, you have to order the size and the strength class of that pipe. So the strength class system we have in Canada is under CSA 50D, 65D, 100D, and 140D. And what those names represent is that's the minimum load that the pipe has to carry before that 0.3 millimeter crack appears. So as an example here, a 1350 100D pipe, the minimum load that that pipe has to be able to carry during that three-edge bearing test, the math is quite simple. You just multiply the strength of the pipe times the length of the pipe times the size of the pipe. So when you take those three numbers, 100D times 2.44, which is an 8-foot standard pipe length, times the 1350 inside diameter, it gives you a value of 329 kilonewtons. Now, most of us don't relate to kilonewtons, so when you translate that into a mass, it's about 33.5 metric tons that you can put on top of this piece of pipe. And the only thing you probably won't even see is a hairline crack. You probably wouldn't see any crack at all because we often over-design our products. That's just the minimum load that pipe has to be able to carry. So it gives you some idea of the inherent strength of the concrete pipe without any sort of bedding or additional support around it. Again, this is a three-edge bearing test, which is almost a point load on the pipe. So it's a very severe loading condition that you'll never see in the field. So I'll just carry on here. Now, to achieve those different strength classes, we actually don't do anything to the concrete different. We don't change the mix design. We don't make the walls thicker. The only things we change is the reinforcing steel. So you guys will get a chance to see a cage up close later. But what we do is we can change the gauge of the wire and the spacing of the wire is one way to do it. but we can also change the geometry of the cages. So for the smaller diameter pipe, typically we have a single cage that's close to the middle of the pipe wall. And then if that's not enough, we will go to a double cage, which has a circular cage at the inner and the outer face of the pipe. And then if that's not enough, we'll introduce a third cage, which is an elliptical cage, kind of sandwiched in between the two round cages. And you can see it's touching the outside cage at the spring line and touching the inside cage at the top and bottom. And that's because that's where those tension zones are, where the steel is required. You don't need a lot of steel in the compression zones. So that's what we try to do, is try to use that cage efficiently by making sure that it's located in the areas of the pipe that we need. Now, the important thing with this scenario is you always have to know where the top of the pipe is now, because you don't want to install it with that elliptical cage rotated in any other way. But the thing about this is typically this design is used for large diameter pipe, and large diameter pipe typically has those lifting anchors that are cast into the concrete. So those lift points are telling you where the top of the pipe is. Now, as far as crack evaluation goes, we as producers, we get sent a lot of CCTV videos and asked to assess what's going on there. So some of the things we look out for is, one thing to keep in mind is if concrete is wet, even fine cracks look a lot bigger because it looks kind of magnified. The other thing is some cameras may distort things. There's a certain size of a camera that you have to use depending on the size of the pipe. So that's one thing to keep in mind. The other thing is some cameras have really good zoom functions, so they can zoom right into a small crack and make it look huge if you have no sense of the scale of what you're looking at. The hard thing about any crack is it's hard to know if that crack is dormant or active. So that's important to know as far as how quickly should you rehabilitate a crack. If you know that it's active, maybe you wait till everything settles and it reaches an equilibrium, or maybe you have to act quickly because things are starting to move and things are getting worse very quickly. So active and dormant cracks, that's a tough one to assess, but that is a good thing to know. And then the other, I would say the biggest problem is confusing appearance with function. This is a sewer pipe. It's not the face of an office building or the floor of a shopping center. It's a sewer pipe that's been handled multiple times. It might have been dropped. It might have been kicked around, and it's now in the ground. So you can't expect the concrete to look pristine all the time. It doesn't mean that it's not going to function as a sewer, though. Now, forklift marks inside the pipe is pretty common. That's the way most of us handle our product in the yard. We slide forks in and can handle 2 or 3 pipe at a time. Oftentimes those forks may scrape along the inside of the pipe and leave a mark. A lot of times those are mistaken as cracks. So again, we try to figure out whether that's a forklift mark or a real crack. Typical cracks are pretty jagged through the concrete, where if you see sort of a smooth line in the concrete, it's likely from a forklift. So that's one thing we look for. The other thing is just poor handling practices often cause damage to the pipe. You can see in this example here, an excavator is being used to pick up the end of the pipe, and it's gouging out little areas near the joint. And so again, a lot of poor handling or even storage practices could cause damage to the pipe before it's even in the ground. Now in this scenario here, this is what the designer is typically designing for. It's the final resting spot of that pipe. But the reality is there's temporary construction loads on those pipes during construction. So you might have very little cover over the pipe, but you have this heavy equipment driving over it, and that's what caused a crack that you might see a couple of years later. This is the longitudinal crack is what we typically expect to see. Basically what that crack represents is the concrete has now transferred the stresses to the steel. And the evidence of that happening is a little crack there. So again, seeing a crack at 6 o'clock and 12 o'clock of a pipe is not a problem. It's what we expect. That's why we put steel in the pipe, because we know that's going to happen. So again, those are in those tension zones that I highlighted before, 6 o'clock and 12 o'clock on the inside face. Now, circumferential cracks is something that is not very common, so a lot of engineers get pretty excited when they see those. But really, structurally, a circumferential crack is not a problem. It's no different than a joint to have a crack, 360 degrees around the barrel. There's no structural concern with that pipe, but it is good to understand what causes it. So there's two types of circumferential cracks. There's a broken back and a broken belly, and I'll just explain it with this poster here. Typically, circumferential cracks we see in small diameter pipe where the bells are flared out. Now, this is how to properly install one of those pipe, is you have to dig little pockets in the bedding to transfer all the support to the barrel of the pipe. You don't want everything bearing on these bells. So you dig out these pockets, you put all the support on the barrel of the pipe, which is the strongest part of the pipe. And that's a sort of an ideal or the correct way to embed the pipe. Now, oftentimes this is what happens. You end up with a well-compacted flat surface. You put the pipe directly on top of it, and you can see now there's no support under the barrel, and all the support is on the bells. Now, you can also have this scenario where it's very uneven. You might have some boulders mixed in there, putting all kinds of point loads on the barrel or on the pipe. And that's what typically causes the circumferential cracks. Now, other types of cracking that you might come across that's not very common is a shear crack. That's usually caused by the support under the pipe is not even on either side. So that's when you get a sort of a diagonal crack through the pipe wall. Again, not a common occurrence, but it could happen if you're not careful with the installation. Another type of a crack you might see is what's called radial tension. And that's where the pipe, for whatever reason, is overloaded, or maybe the strength of the pipe wasn't enough. And what happens is the inner cage of that pipe wants to deflect. It's trying to straighten out at the bottom because it's being overloaded. And when it wants to do that, it actually spalls all the concrete off at the floor of the pipe. And so when you see that happening, that's probably what's going on, is either the pipe was overloaded or the strength of the pipe wasn't enough for the loading condition it was designed for. Joint problems are pretty obvious. A lot of times we see joint problems from this scenario. When the alignment of the pipe isn't quite right, the contractor uses the excavator to try to force it down. And that could cause some cracking around the joints. You can also have pinched gaskets that obviously will lead to leaks because you should never see the gasket from the inside of the pipe. If it's installed properly, and we'll touch on gaskets in one of the other stations there, but if it's installed properly, you should never see it from the inside of the pipe. So this is an example here where there was a leak. As you look closely at the joint, you see just concrete there, which is what you expect to see. But over here, you see a little bit of the gasket peeking in. So that tells you that the gasket has been moved or pinched in the joint and not installed properly, and that's what's causing the leak. But it's pretty tough to see until you actually zoom right in and look at it. Infiltration, there's different levels of infiltration. Some are acceptable and some aren't. Sometimes you see a lot of dampness on the concrete, but you can't see where the water's coming in. It might just be slowly trickling in, or it could again be left over from the cleaning process. There are instances where you see a little bit of water moving around through a crack or a pinhole. That needs to be addressed depending on the application. And then you have the gushers where it's just under pressure and it's constantly coming in, and obviously that needs to be addressed. And then the last thing I wanted to leave you with is something that we call autogenous healing. When you soak concrete with a crack in it, oftentimes what you'll see is this white crust that's formed. And basically that's just evidence of the concrete healing itself. So it's no different than when you cut yourself and you have a scab. That's basically a scab in the concrete, and you should just leave that alone. The concrete has healed itself. There's no issue with it. Again, it's not pretty to look at, but it's inside a sewer. So our recommendation is don't disturb that. Just leave it alone. And so that is something, in one of the samples you'll see some evidence of that happening, because it was outside and got rained on or whatever. So that is something that is often misunderstood as well with concrete. Bram will take you through the display here and show you a few of the features that we talked about.
So this guy here is kind of evidence of a complete failure of a pipe. And this is, like, you can see the cracking has gone right through. It's very wide, especially in the middle. It looks like the cage has tried to flex more than the concrete will allow, and it started popping pieces of concrete out. This guy here is a bit more sedate. You can see the crack at the bottom is really the worrying one. He's got a diamond here to show the width. So this is past 0.3. This would constitute a fail that would need to be repaired. And this kind of depends on the situations, right? If it was above ground, for sure repair it. If it's in the ground, you kind of have to watch it, what's actually happening first. And if you look at the back here, you can see the spigot has cracked here. This crack here, it actually looked worse yesterday. It's starting to come back together. But the spigot always looks a bit worse. And I've tested these on hydrostatic. Water will come through there, but fairly slowly. And this guy here, this is a crack that is at least close to 0.3. I don't think I would call it 0.3 because you can't really get the gauge in multiple places. And this is that crack we talked about earlier with the water in it. Like, you can see it's not that bad a crack, but you can see it from very far away. And if you look at it here where it's cut open, it tapers off fairly quickly. It's mostly near the surface.